Welcome everyone. So, today we are going to discuss on physical synthesis. So, in specifically we are going to talk about all the sub steps of physical synthesis, partitioning, floor planning, placement and routing briefly. In physical synthesis, if you want to cover, it might take maybe 20 lectures. So, instead of going into detail or each techniques in each techniques detail, what I am going to talk about in this, I will try to give a brief overview of the whole physical synthesis process, what is the objective of each sub steps and what is the problem definitions and what are the generic way to solve that. So, instead of going to solving them using exact algorithms. Okay. So, let us start. So, if you look into VLSI design cycles, we have seen that we have already discussed that it start from some specification, then it go through high level synthesis, logic synthesis, technology mapping and then physical synthesis, fabrication and packaging, right. And we already have discussed about high level synthesis, logic synthesis and technology mapping, and we are going to talk about physical synthesis today. So, if you just think about after the technology mapping step, what we have? You have a transistor level or sorry gate level circuit, which have is a huge circuit, and those are actually represented by the cell libraries. If it is FPGA, then it might be this LUTs, RAM, DSPs, or if it is ASIC, then it is the library elements like NAND gate, NOR gate, basic flip flops, RAMs and all, right. So, this is something the representations. And now, in physical synthesis, what would be our objective? We have to give a physical form of your chip, right, because so far we have talked about lot of optimization, synthesis and all those stuffs. Now, we have to give a physical representation of your design, right. So, which is important, and now what do you mean by physical synthesis? Physical synthesis in the sense that now you have to place all the your gates or those gates which actually will be converted to transistors in this physical synthesis, and then they will be placed right in your actual chip area, and all the interconnection, all the edge between the nodes, that has to be connected physically in your within the chip layout area. So, that is what is called physical synthesis. In the physical synthesis, you try to place those nodes or the basic units of your design into the physical area, and also we try to connect them properly, and your objective is always try to find out the minimum area to pack all of your gates in some in a layout, and you try to make the interconnection cost as low as possible, right. So, this is the basic overview. Once this is done, we will go for fabrication, and you also remember that at this point this gate level design will be converted to transistor level circuit, which is very obvious transformations, because it just replacement of equivalent circuit representation of each gate, right. So, that is not a big task of physical synthesis. So, we can easily convert that gates to the transistor level circuit, but what is important here is that making a physical placement of those gates and then making physical interconnections, right. So, let us go into this physical design steps. So, in physical design the sub steps are partitioning, floor planning, placement, routing and finally, the compaction. So, we are going to talk about this partitioning, floor planning, placement and routing, what is that and what is the objective of each sub steps, right. So, if you look into this design, so when you have a big design, so first thing we have to do, our objective is to, suppose your design has say 1 million gates. So, we want to place them, but we try to placing all this 1 million at a time is kind of impossible job, right. What is the basic approach we usually follow in every life? So, whenever you have a big task, we try to make it, we partition it, we try to make it sub task, and we try to solve the sub task, and then we try to combine the result. So, the same approach is happening here. We want to place the whole thing together into the layout area. So, we instead of doing that, we try to partition the whole thing, right. We make the small component, we want to place each component at a time, and also it is kind of a hierarchical or recursive approach. So, suppose if you have the big circuit, we want to place partition in say 10 components. So, then I place these 10 components in the layout, then each component we again break it, and we again try to place each sub component of our component again, right. So, it is kind of a recursive approach. So, the first thing of this process is that you partition your big design into small components, so that you can place those each partition, right. So, that is what is called partitioning, right, or clustering. And then what is the floor planning and placement is that when you have this each component, that has to be also placed, right. So, that each component has to be placed in your area, right. So, this is what is called placement, floor plan and placement. The floor plan and placement I am going to talk about detail. So, basically you plan your floor. First of all, if you have say 10 components, how you should place, this can be placed this way or this can be placed this way also, right. I mean, you can think about either vertically or horizontally, right. So, similarly this can be placed this way in the or the vertically as well. So, you can have lot of possibilities, and maybe some other organization give you a compact area instead of this organization. So, this floor planning and placement take care of that. Once you have the small component, the partition, those has to be placed properly, so that your total area is minimum. And then this pin assignment is something. So, as you understand that from this component there will be many interconnection going to some other places, right. It may go to these places, this may go to these places, this may go here, this may go some other places, right. So, there are a lot of interconnections. So, that is what is. So basically if you have a gate, that will try to communicate, right. So, you have to assign some pin, because now you have a make an interface for this module, right. So, whatever the interconnection from here is going out, that will go through some pins, right. So, these are the port kind of. So, you have to assign pin for each component, which is called pin assignment, and then you have to make the actual connections, right. So, then once you have this, then you have to make the global routing. So, for example, you want to make the connection from this node to this node. So, you decided that this will go through this part, or it may be in some scenario it might go through this also, right. It might go through this also because of some reasons. So, that is what is called routing. So, you know that I have to make a connection from this port to this port, and you can understand for a bigger layout there may be multiple such possibilities, right, and you have to make this connection exact, right. So, through which part of the channel it should go, that you have to decide, that is what is called global routing, right. So, then once the global routing is done, then you have to make the detailed routing. What is that? So, detailed routing is something once you have decided that there are 4 wire will go through this portion of the design, then you have to decide which, there may be some track, right. So, this track this will go, and the second track this will go. There may be some track which can be shared by 2 components. We will discuss about those detail. So, which is called detailed routing. So, that you understand the basic essence of this whole process, that you break your big design into multiple component, which is partitioning, and then you decide for each component what is the exact area, and then how to place them optimally, so that your interconnection cost will be less, and then you make the actual connection into okay. The previous, that is pin assignment, you make the point of your how many pin you require to make the interconnections for each component, and then you go for global routing. Global routing means you try to make the actual through which region your particular wire will go, that you will decide, and then you make the actual detailed routing, exact track through which that particular connection will go. So, that is what is called detailed routing, and this is the overall steps of your physical design process. Okay. So, what is the problem or the difficulties in physical synthesis? It's basically, you can see that the number of transistor may be 100 million, 10 million, it's a huge, right, and handling such scale design is not easy, right. And also sometime you have that performance driven design, something like you want to achieve this timing like this, your power dissipation should not go beyond this, your area should not go beyond this particular. So, you have to always meet a target, right, which is performance driven. And also, as I mentioned, power constant also there. So, you cannot use arbitrary powers. If you have very long interconnection, that will consume low power, so I mean lot of power. So, you have to always also think about that your power constant also meet, and also the time to market. So, you cannot just take infinite time to just do the physical to get a generate a physical chip which is optimal. So, you always have a time to market or constant, or the pressure always from the marketing team, you try to finish your things within the time budget. So, that is why this physical synthesis is very a complex process, and when it has to be and we will discuss all these sub steps, and there are a lot of methods are there. And also one more important point has to be noticed here, that all these subtasks that I talked about, this placement, floor planning, global routing, physical routing, all are most of them are kind of a NP complete problem. NP complete problem in the sense they do not have a polynomial times, they are not polynomial time solvable. They are kind of exponential. If you have to try to find an optimal solution for them, you need an exponential algorithm, right? But physically you can understand with 100 million transistor, it just won't work, right? So most of the cases you have lot of heuristics. So that's why basically this in physical synthesis you find lot of approach. They all are kind of heuristic based approach, because all exact solution is not scalable. You always have to think about some heuristic which is logical, which works for most of the cases, right. So that's why there are a lot of variations of the algorithm available for this each subtask, and it might cover the whole semester to just to discuss the physical design, right. That is also another part of this the complexity of this physical design, right. So now if you move on, why and you can see that this physical synthesis, all the tools are available, industry tools are available, right. So they are already matured, they are working fine, and then why need to think about more on this physical design, why this is still relevant. So the point here is that yes, the placement, all those things are available, but since you understand they are suboptimal, they may not work always, right. And most importantly, the new whenever this as the things as time move on, the new complexities are coming up, right. For example, this reliability of your chip, you try to interconnections are going very high nowadays, and your and also this crosstalk you want to minimize. So new reliability of your design, and security is also a big concern nowadays. So all these new aspects are coming, key aspects are coming nowadays, and you have to develop, or you have to emerge with some new placement algorithm or partitioning algorithm that should actually support this kind of new requirements of your design. So for example, the security is something is very important part in important issue nowadays. You can think about the recent news on that processor, the processor that almost all Intel processors or AMD processor are not, they are vulnerable to attack, right, because of that branch prediction. You might be aware of that they might leak some information from that power, which can be about the software that are running on that, and some attack can attack can happen to your processor also. So basically the kind of algorithm that so far developed, those are not concerned about that. So just to this is just to give the highlight that you might have to think about new kind of placement or new kind of partitioning approach. That might be some new security concern will come because of the existing approach, right. So you have to always try to think of evolving new kind of technology or the algorithm or the technique that can support this new kind of constants, right. So this is also, that is why still this physical design is relevant, and we always still talk about those these synthesis steps, right. Okay, now I will move on to each substeps. In each substeps, what I am going to do, I am just going to define the problem and discuss the issues, and then I will, without going into each all this existing algorithm on that. Okay. So we will start with partitioning. So partitioning is something very common in every approach, right. If you just think about it's just the ASIC prototyping. What we do actually, we have a big system, right. This might be a HAPS board, right, and so where we just stack multiple FPGA, there are multiple stack, right. So I want to map a big processor in a FPGA board, and it's not fit in one FPGA, it might need 100 FPGA. So that is how we stack, right. So we have some multiple layer, and then each layer we have multiple FPGA, and then we probably, and each of them is kind of FPGA, right. This is just an example. So similarly, whenever you have a big problem, we try to partition it, and then we try to merge to get the solution, and that is what is also the same approach we are going to solve in this partitioning of a circuit, right. So whenever you have a big circuit, our objective is finally place all this. For example, here this is a big circuit is given, our objective is to place all these gates in a chip area, in minimum possible area. So one approach is that you take one by one and you place them, which is not physically possible, that I have already discussed. So basic idea is that partition your design, right. So you partition your design in small component, and you try to place this together, 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 something like this, right. So similarly, this is what you are shown is there. So we have a partitioning here. we have a partitioning here and we have this the 3 partition, and I try to place this partition independently, right. And once we have done, I can again recursively do the same partition within this component or say in this component, unless I have a module which is actually easy to handle, right. So, this is what is the partitioning of the circuit means. We have to partition, and whatever the things we have to take care here is that this cut, whatever the number of wire crossing this cut, right. So, if you make a partition here, we have to identify how many wire is crossing, right, because those wire has to be routed later, right. So, because you understand when you have this break these things and you have a say there are 3 component as I shown here, and now all the connections that are coming from this crossing this cut has to be routed here, right. So, they have to route it here. So, that means your objective will be you have to try to find a cart which has minimum number of such routing logic, right. So, that actually give you the benefits that you have lot of less interconnections, and that is a good partitioning of your algorithm. So, that is what is important. So, if you just formulate the circuit partitioning problem, so our objective is something to try to bipartitioning. So, basically if you think about the partition can be anyway, right, it can be k partitioning, you can do part in k components, then it is a k partitioning. If it is bipartitioning, you try to make it bi. So, you can do a recursive that I break the whole circuit into 2, then the other thing will be again split into 2, and this is kind of a bipartitioning, right. So, this is the whole circuit, I make it by 2, then this component again I make a by 2, this one I want to make a by 2, then this component I make a by 2, this also I make a by 2, and so on. So, this is what is called bipartitioning, where I am going to partition the whole design recursively, right. And so, if this is I say partition into 2 component x and x bar, and this is my cut. So, what will be our objective? Our objective is to min cut, the number of line crossing here should be minimum, that may be your objective, or it may be that you try to make a bipartition into 2 partitions where the number of nodes in this component and number of component is same, which is called minimum bisection. That is actually the bisection where the number of element in the both partition exactly same, right. Or you might have a minimum cut ratio. What does it mean? It may be that the number of wire component crossing here divided by the number of node here into number of node here is the minimum, right. So, your objective might be different, but apparently the main objective is something you try to reduce the number of wire crossing that. So, crossing in this cut, which is something will be finally has to be taken care of by the routing algorithm. So, that will be our primary objective, right. So, that is something this is how we can define the partitioning problem. So, one point here to be noted that your graph, I mean usually in a graph we consider the node between edges, right. So far we have discussed that, but whenever you have multi fan out, right, this AND gate output is going here and here. So, then how do you represent this node, right? This is something called hyper edges, right. There is one source and multiple output. So, this kind of edges is called hyper edges, where you have to represent the edges between set of nodes, right, where the first start node is the source and the rest are the destination, right. So, here A, B, C means A is the source node and B and C is there, right. So, this is something like this. So, this is how we can represent the hyper edges. So, you can argue that I can actually put 2 edges here like this is also representing the same thing, but it will create the number of edges is more and it will create things complicated, right. So, usually we handle this hyper edges usually Steiner graph, right. So, we actually think about this, I can put a node here and this will become the same thing. This is a Steiner node and it will be a Steiner graph, and if it is only 2, but it might have a 100, right. So, then it is actually this is something we can represent like this as Steiner. We will discuss about this more detail later. Okay. So, here as I mentioned that formulation is that I want to find a cut such that between 2 partition either it will be minimum cut, the number of crossing is less, or the bisection have is exactly bisection that the both component has equal number element with minimum number of cut here, or I can have a minimum cut ratio. So, here is an example, suppose this is my graph where this 4 means the number of edges between this to this is 4, right. There may be more number of edges, I just pick the count, this is 100 means the number of interconnection between D and F is 100, right. So, min cut is this, right. So, if you just think about a cut here, how many node are crossing? 100 plus 100 is 300. If I make a cut here, the number of node are crossing 4 plus 9 13. So, this is a minimum cut, right, and this is a minimum bisection, because now if I make a cut here, the number of node here is 3, this is number of node is 3, right, and this is what is the minimum cut ratio, because here the number of node here is. So, if you make a mid cut, this part of the circuit has 5 nodes and this part of the circuit has only 1 node, right, whereas here if you make a cut here, I have a number of nodes in this side is 4, this is side 4, right. So, as I mentioned here is that min cut. Why this is min cut? Because the number of node is crossing here 2. You can think about this is also min cut, number of node is crossing here is 2, number of edges is crossing is 2, but the weight is 19 here, this is 13. So, this is the min cut, right. There is no other cut where we have only 2 node passing, right. This is min cut ratio, because in this case the number of node is 19. So, this is 19, and this is the bisection where, because this side is also have 3 nodes, this side is also have 3 nodes, and the number of node is crossing 100 plus 100 plus 100 300, right. So, there are 300. So, your partitioning is something like this. You always try to partition it. It may be repetitive, or it may be you may in general you may actually partition into k partition, as I example here when given formulation here. You may have tried to partition into at exactly in the same time in k partition, such that each component area, there might be some area requirement that each component area is within the permittable size, and the number of edge crossing there, the cut size is always also the crossing, that each cut should have at least this, I mean it should not go beyond this particular number of the cut size should not go beyond some I. So, that constant has to be modified, and also you try to minimize the total cut size, right. So, it is something like this. If you have a big circuit, you try to break into k partition like this. So, this is partition 1, this is partition 2, partition 3 or something like this, and each part of the partition should satisfy the area constant, each cut should satisfy the minimum maximum possible cut size requirement, and the total number of edge crossing each cut should be minimum, right. So, this is what is called the in general circuit partitioning formulation, right. So, in partitioning, as I mentioned, this is NP complete algorithm. We can have various kind of approach. It can be iterative, that you try to do one partition one at a time and then move on, or it can be module partitioning versus net partitioning, or it can be multi-way partitioning, multi-level partitioning, or it can have a timing domain partitioning or so on. So, there are maybe various kind of techniques are there, and also if you just go into this approach like iterative improvement algorithm like Cunningham-Lin algorithm, Fiducia-Matthews algorithm, Krishnamurthy's algorithm, similarly simulated annealing approaches are there. So, there are various kind of approaches are there. It is not possible to discuss all of them here. I just give you a brief overview of the scale algorithm, so that you understand how this practical and this is the most simplest version of the algorithm, believe compared to the other one, right. So, that will give you some brief idea how the partitioning works, right. So, if you just move on. So, this is actually do the bisection, right. So, basically try to make the circuit into by 2, right, and the idea is that you start with the initial any arbitrary partition. You take a just any arbitrary partition, you try to bipartition the circuit, and then in each iteration you try to take a node here and you try to knock a word here and you move it here and you try to move it here. So, that after every iteration the number of node here and the number of node here is remain same, right. So, here is, so basically if you think about initially my my graph has 2 n nodes. After the partitioning, each component has each partition have n nodes, and every there are m number of edges. So, that there are it actually defined into 2 partition into this is x component, this is y component, this is also n node, this is also n nodes, and so and then you try to minimize the cut cost, right. So, this is what is something the total edge cost is minimized, right. This is how the whole thing works. So, so if you just think about how it should work, you might try to all possible partitioning, right. If you make a trivial approach, you just make all possible bisection of your circuit and then you find the best one, right. That will be a very trivial approach. Now, you think about there are 2 n vertices. So, all possible combination is n to the power n, right, which is huge, n to the power n possible bisection is possible. And then you just think about 4 vertices is fine, there are 3 possibilities, but if there are, if your node has 100 vertices only, the possibilities is 10 to the power 28, 5 into 10 to the power 8. So, which is huge, you can understand the element. So, even for only for 100 vertices, it will take 10 to the 1 into 5 into 10 to the 13 years. So, which is something infeasible, right. So, which is infeasible, right. So, just to if you want to try to 100 million possibilities, sorry. So, for 100 million possibility, you need this much of time. So, this is just the some numbers just to give you the value that you cannot just go for any brute force approach, right here. So, so all possible finding all possible bisection and finding the optimal one won't work, right. So, in this KL algorithm, the idea is that you the cost you have to understand that if you, so suppose there is an initial connection, you try to move a node from here to here, what will happen? So, whatever the node from this node to the other side, right. So, those node will become, they will not be in the cart, right. So, here I move A to here A. So, these two edges are coming here. So, they are not part of the cart, but whatever the connection from this node to this side, those will be the part of the cart now, right. So, that is the cost. So, which is basically that the external cost, that is this whatever actually crossing the other part and minus the internal, right. So, this is the gain. If you move a node from this side to this side, the gain will be this, right. So, for example, for A initially there are 2 connections to the other side. So, 2 and there is only one connection to this same side minus 1. So, if you just move A to this side, you have actually cart side will be reduced by 1, your gain is positive, right. So, similarly, if you move this B from this side to this side, you can see, so for B there is a connection here 1 and the connection here. So, it does not have any gain. So, if you move B from this side to this side, effectively there is no reduction in the cart size. Now, if you take a 2 nodes, so the gain of A is given by dA, which is calculated by this equation. This is the dA, the cost, and then this cost of dB. So, that means you are moving A from this side, B from this side, cost of moving this plus this, that will be your gain, minus the interconnection between these 2 nodes, right, the interconnection between these nodes, because they are actually counting 2 times here, right. So, you have to just remove it. So, they will always remain the same. So, that is what is your actual switching between 2 nodes is the overall gain, right. So, for example, if you just swap A and B, overall gain is -1. So, which is basically negative. So, it is not a good choice to swap A and B, that means moving A from the left side to right side and moving B from right side to left side, which is not a good move. So, the idea is something, you start with the initial cart, you take arbitrary cart, right, of the circuit that may be high, then there are n nodes here, there are n nodes here, and then you find out all possible partitioning. So, there might be n square pair, right. So, for each there is a node. So, suppose there is 1, 2, 3 here, 1, 2 and 3 here, A, B and C, there are 3 nodes. So, the possible partitioning is into this n into n, 3 into 3 9, right. So, you can take 1 A, 1 B, 1 C, similarly 2 A, 2 B, 2 C and 3 A, 3 B, 3 C. These are the all possible possibilities of pair, right, because our objective is now is to swap 2 pairs. So, you find out all these n square possibilities and then you chase the best one, right. You take the best one which has the maximum gain. So, for each pair you calculate the gain and you actually swap has the best gain, right, and then you log that too. So, that is the gain of that particular move. So, then you just do this for n times. So, you actually make n moves. So, that at least some n nodes are from here, it will move here and n nodes from here moving there, some happening here, and then maybe some of them are actually have a negative gain, right. After some time your gain may be negative. So, you try to find out some k value. So, you make a n moves, but you take the first k gain iteration which actually have a positive impact. So, you make those them fixed, other you just other swapping that you done, you just undo them, right. So, that will not be actually have done. So, this is after this iteration you have another solution, right, and then you will keep doing this until I do not find any no improvement, right. So, this is one iteration. So, the overall algorithm is like that. I make initially by partition, then I do n swapping, right, based on the maximum gain to minimum gain, and then I took only k gains which is k swapping which actually have a positive, total summation is positive, and then others I will just discard, and after that I will get another solution, right. So, the cart side will be improved, and then I am going to do the same process k times or sometimes, unless I do not find any much improvement. So, this is just an idea of this scale algorithm, which actually Cunningham algorithm just doing by bisection or bipartitioning, where by swapping these two nodes. This is just one approach. There may be various approach and there are various kind of technique. As I discussed here, the complexity will be n square compared to the n to the power n. So, which is, and for a better implementation you can have a n square log n. So, so this is also one way of doing the partitioning, bipartitioning, and we, as I mentioned that there are various approach. I mean, I am not going to covering all of them. Now, I will move on to the floor planning. So, what you see after that? So, after partitioning you have some components, right, some partitioning component like this, and now you have to think about the planning your layout area, right. So, you have say 4 components. Now, you have to physically place those components here, right. So, that they are so that your total area is minimum, right. So, you have to place those components here, and you understand their area is not always same. This may be only say 10 unit and this may be 100 unit, this may be 12 unit, this may be 50 unit and so on. So, their area may be different, right, and so that means their size is not exactly all square, right. So, this may be a small thus 10 means is this is small, this is a small one, and this is 100 means this is a big one. So, their size ratio is also different, and most importantly their aspect ratio is not fixed yet. So, I just give you say 100 you can actually construct of 10 into 10, right. This may be say 5 into 20 or maybe exactly square, where is 10 or maybe 4 into 25. You can have a different aspect ratio, right, because I just told you ki I have a block which has only 100 unit. So, now you have to fix this aspect ratio, so that for 100 should I choose 10 into 10 one is better, or 5 into 10 is better, or 4 into 25 is better, and other options are also there, right. So, you have to always you have to decide the aspect ratio of each component based on their total area, so that you can actually compact those all the component in a minimum possible area, right. Because if you just think if you take this kind of which is basically rectangular one, that will cover this portion of the say area, and then you can probably you are not able to fit say another component here. Instead of, if you take this say 10 crosstron, if you place this way, probably other component can be placed here, right. If you do not place anything, this portion will remain vacant, right. So, you try to, and that is called dead space, you try to reduce those dead space. So, in partition this floor planning, what we do, we try to finalize the aspect ratio of each component, and then we try, and our objective is try to pack everything in a minimum possible area, so that your total area is minimum and total dead space is also minimum, right. So, if you just move on. So, floor planning is the problem of positions, finding the plan the position, not exact plan fixing the block, that is important, because I am just planning the positions, right, and then shape is finalized at the beginning of the design, right, where your objective will be optimize the area, total wire length also, because you try to, because I know that now what is the connection between two component based, because that is given by the cut size. So, that if you have a say this block here and there are a lot of connection to this block, you should place this block as close as possible, so that this wire length will be less, right. So, you try to place very connected two component which very close by. So, that your total length is optimized, or delay of the critical path is minimized, routability is possible, that actually physically all the connection can be made in the physical die. So, that may be also your objective, or other objective like you reduce the noise or the heat dissipation or crosstalk between the router wires. So, those can be also your objective, right. So, that is what is floor planning. So, if you just define the problem, so you have n blocks of size area, I know the only area, and I also have some aspect ratio bound, that if you have a say 110 is the your length may be minimum say 6, right. So, you have to find the W and L, right, width and height, W and H. So, your width should be greater than 6 or say height less than 10, right. If you have given those kind of ratio constant on the aspect ratio, that you cannot just take a very long or very short I mean short height or short width kind of things. So, you should have some minimum constant on the ratio, right, I mean this aspect ratio. And then what is the output? You try to actually find out some location of this particular block, such that and you also find the width and height of the block, each block, such that total area is minimum, and also all this height and width satisfy the aspect ratio constant given to you, and your objective is something to optimize the circuit performance. The performance may be one of them, right. So, this is what is the problem. You are given a components where the area is given, and also and the aspect ratio of height and width is not fixed, but there are some restriction might be there, your height and width should not go beyond this or should not be at least this kind of thing, and you try to find out try to place all the blocks in a physical area. So, with coordinate of each block, and you also find out the aspect ratio, that means width and height of each block you try to finalize, so that total area actually fit into this area target, and you have some optimization goal like optimizing the total area or optimizing the routability, interconnection cost and others, right. So, this is what is the floor planning problem. So, as I mentioned this I mean bound on aspect ratio is something that we can always pack everything tightly, right, because the problem I just discussed about, suppose this is your component blocks are like this, right. So, suppose there is one block like this, one block like this and one block like this. Okay. There are 3 such blocks. Okay. So, now if you try to suppose this is your chip area. So, now if you just place this one, say this will take this if this will take say this is A, you try to place this here, what will happen here? Now, suppose this will take in such a way that now this is cannot fit in here and this may not fit in here also. If you just place one of them here, say suppose this so this is say this block is something like this. So, their length is more than this. So, they cannot be placed this way. So, suppose this is B, I want to place this way, right. So, now what happened? Now, there is no way to place C, because it is all fixed, that there is no place. Then basically, you have to just increase the area of your design, a chip area, just to place this C here, right, C here, and many space are remain vacant, right. Whereas, if you just say instead of taking this, if you just take another version of A, which is little bit of this shape, then probably what you can do, you can probably fit the whole thing into the old area. So, this will be your A, this will be your B and this will be your C, right. So, A, B, C. So, this is what is the problem, right. So, you might have a different aspect ratio for which you can actually place them in a smaller area, but if you just have a different aspect ratio, then you might need more area, right. This is a perfect example to highlight the problem. So, one thing always think I just make the width is 1 and the length is like this, right. So, then the problem is that your chip will be just a series of block, right, which is basically just length and which is not feasible, right. This is not something because your layout cannot be just a long strip, which is allowed. So, that is why we have some bound on the aspect ratio. Okay. So, as I mentioned that given the same size can be like this, right. For a same size you can generate different kind of block, right, and also orientation maybe this way or that way. So, you have to consider all possible such orientation given on that aspect ratio constant, and then you try to place all those block in area. So, that your total area, primary objective is to reduce the area size, so that you can actually place all of them in smaller possible area, right. This is what is floor planning. And also we so in general the objective function is the minimization area plus objective length, right. A is the area and B is the L is the length and alpha and beta is some constant factor, right. This is the overall objective of floor planning. Okay. And since wire length estimation is something, because now I do not have the exact placement. So, how can I estimate the wire length is basically just the distance between this so suppose there is a wire from this to this, I can find just the distance from the center point, right. So, this might be your wire length, because this is just kind of a estimation. Okay. So, as I also mentioned that because of your different aspect ratio, it will create a lot of dead space here and there. So, your objective is try to minimize the dead space as well, right. So, this is also will be an objective during floor planning. So, and also there is another concept here is that sliceable and non-sliceable floor plan. What is that? I mean, sliceable floor plan is something. So, you finalize your aspect ratio and you finalize your block height and width, right, and then you place them. So, after placing one is sliceable means what? You can actually can obtain your floor plan can be obtained by repeatedly just slicing the things horizontally or vertically. Suppose this is how you are placing your design. So, this is A, this is B, this is C, this is D, this is E, and this is F, and this is G, right. So, this is your placement. So, then what is slicing? So, I make a slice here, then I make a slice here, I make a slice here, then I make a slice here, then I make a slice here, and then make a slice here. So, I just bipartition each component totally, and then this is sliceable. On the other hand, if you just look into this one, so this is not a sliceable one, because you can see that I cannot make this kind of partition. If I try to make it, this will partition here. So, this is my component now, this is also not a sliceable. So, I cannot make this kind of bipartition here, right. So, here I just make a bipartition like this, but here I cannot make such thing. So, this is non-sliceable. So, it is generally good practice to make a sliceable floor plan. So, such way you actually make the connection, so that you can make a sliceable floor plan, and we will see that is actually helpful in that we can see that this sliceable floor plan actually is easy to handle for placement, routing, and all other components. So, usually the kind of floor plan we try to generate, that is sliceable, right. So, what is sliceable? I just repeat again, is something we can bipartition each sub component at a time to generate your layout plan, right. So, this is how you can do. So, any order, right, horizontally or vertically. Okay. So, these are the some terminology that you should aware of during floor planning. So, again this floor planning, you understand there are a lot of such approach, various approaches are there, and because it's again this is NP complete problem, and you cannot have optimal solution cannot be obtained by some optimal algorithm. So, you have various kind of heuristic approaches also available for this step as well. Okay. So, I move on to the next step, which is placement. So, once you have, so basically in what is the placement problem? Now, you actually physically going to place those blocks in your layout area. So, the problem input of this block is that there are say n blocks, and I know because now the shape is fixed by the floor planning, pin positions also fixed by the floor planning, because the pins exactly where the pin will be there, that is also fixed by them, and the nets also given, because you have now let of blocks. So, each block where exactly the pins are there, that is finalized, and for each block is given, and exactly the connections among them, right, from pin to pin the connections are also given to you, right. So, this all are given to you now. So, these are all the inputs, all blocks, their pin configuration, their exact shape, the height and width also given for each block, because now the fixed size is already fixed by the floor planning, and all the nets, exact net where exactly the connections are there given, right. So, now you try to find out the exact position of this each block, coordinate of each block, so that no block overlaps, total wire length is minimized, and area of the resulting block also minimized for a given die, right. So, this is something is the placement problem, and you can see you can have other objectives like this condition like timing, routability, clock, similarly like the floor planning also. These are can be also your optimization criteria. Okay. So, you can see that floor planning and placement is very close by, because in floor planning also we try to find the position of each block, and here also try to find out what is the difference, right. So, basic difference is that during floor planning the shape is not given, only the number of block is given, IO pin positions is also not given, right. So, your kind of the blocks are soft blocks, whereas in the placement I know there are some position is given by the floor plan, but that is not the fixed position, right. So, but their shape is fixed, IO positions are fixed, right. So, this is kind of a hard block. So, in soft block I have other options like I can take a different aspect ratio and try to fit in, but in placement time all the blocks are a fixed height and width. So, I can it is a kind of hard block, I cannot make the any change in the aspect ratio. So, that is the difference between. So, both are actually try to find the position of the circuit. So, it may be that the whatever the floor planning given generated the position of the block, that may be the final one, but placement you try to actually see there can be some other movement can be done without changing the aspect ratio, and finally, it may accept the floor planning positions, or it may try to find out a better placement of those blocks, right. So, floor planning, as also I mentioned that these are also n block, and you try to find out the coordinates. So, you can see the input is almost same for both, right, the set of block, output is coordinates, but the only difference is that IO pins, aspect ratio, those things are not mentioned here, and whatever the floor plan positions find out for each block, that may not be the final one. Placement try to relook to that positions and try to optimize the area. There may be some little bit of movement of the blocks can be done, so that your total wire length is minimum, or you can also remove your total area. But after placement, all the position of each block is finalized, then you cannot have any other change. Then only things to be done here is the actual making the physical interconnections, right. So, after floor planning, there is a possibility just to exchange some block position, or moving to other places is possible without the die area, with an objective to reduce the number of interconnections, total area. But after placement, you cannot have any option to move your positions, right. This is what is after placement. So, you just think about, I just give an example here. Suppose this is your circuit, and suppose this each component is a block now, okay. So, just for a simplicity, and say floor planning decide this particular size, and the total wire length is so if you just place them here like this way, so the total wire length is like this, right. So, if you make this connection here, so if you have to make a connection from 1 to 5, you cannot make a connection like this, right, because it has to go either vertically and then horizontally. So, if you just think about the length of this is 2, 1 and 2, if you count here 1, 2, 3, 4 and 5, 6, 7, 8, 9, 10. So, the total wire length is 10. Now, I just have another placement, because all are of same size here. So, I have all the size, I make a connection like this 1, 3 here, instead of there just swap 2 and 3, and this 5 and 6, 5 and 6. So, this is 6 here and 5 here. So, I make some interconnection changes here and there, and now the total length is 12. Right. So, you can see that even of the same block size, same area, but I can make some swapping, some exchange here and there, so that your total area remains same, but the total wire length may reduce, right, from this to this. This is what the placement try to do, right. The same size block can be swapped, or can be moved to some other places where some dead space are there. So, those kind of things can be do during placement. And also sometime this if you just try to make the connection, you have to see that you cannot have the two connection can cross in the same line. So, if you just plot this block like BC, CA and EF, GH, then you to make all the connection, you need only 2 tracks, right. You can make a connection like this, and you have a connection, they are not overlapping. So, they can be put in the same track, and this connection can be put in the another track. So, you need 2 tracks, right. Whereas, if you have the some different placement A, B, C, D, E, F, G, H, now this connection and this connection cannot be placed in the same, because there is overlapping portion. So, they have to be in 2 tracks. Similarly, this has to be make here. So, I need 1 track, 2 tracks, and then just to B to E. Now, I cannot make B to is there, B to F is there, D to H, okay, D to H I cannot make the connection now, I need another kind of layer, right. So, this is something I need 3 tracks. Just to give an example here is something that even after floor planning, there are a lot of opportunity to just do some reorganization of your block, so that you can actually reduce the total wire length as well as total number of track requirement, right. So, this is what is the objective of the placement step. So, you can see there is some random initial placement what is generated by floor plan. Effectively, the placement looks like this, right. This is just the snapshot of their layout, but you can make some modification. You see the number of wire length become very less here, right. So, you have this is very sparse compared to this dense placement, right, and this is the after final routing. So, you can see that you can actually make lot of interconnections less, you just moving your blocks, right, but during placement. So, the placement has a huge impact on generating the final route interconnection cost, right. So, placement, as I mentioned, it has reason. So, basically, as I mentioned that route interconnection cost is growing more day by day, right. So, the placement become important just to reduce the total interconnection cost, right. So, this is something is important, and the problem with the placer is that now the number of 100 million cells, right. We have maybe 10 million cycle, and we have to also place these macros like this DSPs and all those, and you also have to place the ports, pads, everything you have to find. You have to also find out the limit and the honor the target and limit of each length, net length, respect the floor plan constant and all those things. So, you have to, the placement has to satisfy all this kind of constant. Okay. So, here is also another example, that bad placement. So, these are all components are placed, and this is the interconnection. You can see there are a lot of crossings, right, and here if you just reorganize them, you can have a good placement, the number of wire length is less. So, placement does this. So, make a good placement, so that your total wire length is reduced. Okay. So, again in placement also, since it is also another empty complete problem, you have various approach like simulated annealing, partition based approach, analytical approach, and so on. And we again I am not going to detail of discussing all of them, but the basic objective is understood here. Just to reorganize your placement, I mean repositioning your block, so that you can reduce your total area and primarily total wire length. Okay. So, I will move on to routing now. So, I now the positions of each block is fixed, they are final, I cannot change their position now, but I have to make the physical connection. So, I know these blocks are placed here, this block is placed here, this block is placed here, and I have to make these connections now, right, and this is what is routing. And you can see here I make this connection like this. So, to remember that finally this connection cannot go like this, right, it has to be go vertically or horizontally. You have track, vertical and horizontal track, you have to make the connection through this, right. So, so the routing problem is that it is after floor planning or placement. So, you have a net list, that means each component positions, and the timing budget, that is this for each net it should meet this much of timing, and the location of block or location of pins, and output is that actual geometric layout of the all nets. Okay. And your objective is to actual, this is how where the actual interconnection happening. So, your actual objective is to minimize the total wire length, right, and also the number of vias I will just discuss now, and your also each net should meet timing budget. So, that is what is the routing problem. So, routing this routing problem has to be handled here. So, the routing has two types, first is global routing, the second is detailed routing, and the other kind of techniques are there like clock routing or cell routing, mesh routing, which are not covered here. So, primarily, so initially what is happening here, so here is the things is there, the routing is has two phases, first is global routing, the second is detailed routing. So, that means what I just decide keep from this connection to this connection, this will go through this part of the circuit and through this part of the circuit and through this part of the circuit. This is I decide, not exactly the track, through exact which track it will go, so which is called global routing. So, in global routing I just decide through which part of the circuit or which are the channels through which it will go, that I decide. For example, just for example say for this I just decide it will go through this track plus this track, something like this. So, that is what but I do not finalize the exact track number here, and what is done in the detailed routing. So, it has two phases, global routing and detailed routing. So, again this routing can have two approaches. In sequential approach you take a one net and you try to route that one at a time, and maybe after some time you end up a situation that the routing is not possible, maybe one of the channel is over congested, you cannot put another signal through that. So, you can actually rip up and reroute, that means you ignore some of the things, you move back and again restart placing to somewhere. So, this is a sequential approach, or in concurrent approach also you can take all the nets simultaneously. I will try to do them at the same time. Okay. In the routing, as I mentioned, the primary is global routing and then detailed routing. Global routing has different kind of approach. In detailed routing also general purpose, in a smaller case we usually have a mesh routing or line search. In a restricted one I can have a channel routing, switch box, over the cell and river and so on. And for channel routing we usually apply left edge algorithm, greedy algorithm or hierarchical algorithm. I am not going to detail of them. And the specialized one like routing the clock or the power rail of your circuit, right. So, if you just go into the, I will just define the global routing problem now. Basically the global routing has three phases, that the region definition, region assignment and pin assignment. Okay. So, what is the region definition? So, so basically when you have a channel between, so the part of the circuit which is basically between two blocks which is called channel, So, this is also a channel, and you have this is also a channel, and this is a switch box, because this has multiple port, right. The data can come from this side as well as this side. So, it has more 4 inputs. So, it has only data can come only from this port will have only 2 sides, that is channel and that is switch box. So, based on that routing area, you decide the channel number. You have to basically define the region that I have in this graph. I have basically 3 channels. I have 3 channel and 1 write, because after this detailed routing I have to say this particular connection go through, this is a channel 1, this is channel 2, this is channel 3, and this is a switch box 1. I have to say that I have this connection goes through this to this. So, that means it is covered to C1 switch box and C2. Then whenever I am going to detailed routing of the channel C1, I have to take care of this node, right, this particular connection. So, this is what is something. So, basically I just assign the first I have to define how many region are there, how many channels are there, how many switch box are there, that I am going to decide first, which is region definition, and then this is the so for this is just to say is that for get array, that is FPGA, this region is something like this, right. So, this is what is the regions, because they are the interconnection area is very fixed. Standard cell I have to make a connection from this to this, the feed through. So, these are the channels, right. And for full custom, where you have all the option, you can have a switch box and channels, and all the possibilities will come, which is the ASIC design. Okay. So, after that, as I mentioned, the first is region. You define how many channels are there, how many switch box are there, and then you make the actual connection, and you assign this region assignment. This particular net go through this switch box, this switch box, or this switch box, or these regions, right. This go through this channel, or this switch box, something like this. So, you have to assign the channel and region or switch box to each net, which is called region assignment. And then this let us forget about that. And then the finally after this is the pin assignment. Pin assignment is something you then finally, as I mentioned here, after that you actually make the pin assignment, because what is happening here, once you finalize one particular channel, you know how many pin are there, how many pins are there, right. Similarly, for this I know how many inputs are coming, how many pins are this side. So, that is what is called pin assignment. So, after this you decide the pin of this pin assignment for each channel or the switch box, and once this is done, I am going to go for this detailed routing. So, you can see that suppose this is one my channel, I know for this particular channel 4 pin here, right. So, these are the pin positions, these are the pin position, and I know that I have to make a connection from this to this pin, or maybe this pin to this pin, and so on, right. So, I know the pin configurations and all those. Then I have to make actually the actual connection in this channel at a time, so that I can reduce the number of track here, right. So, that is what is called channel routing problem. And whenever you have switch box which has connection from all 4 sides, that is a switch box problem. Okay. So, as I mentioned, then again the one important concept here is channel routing, so channel ordering. So, suppose I have to decide the width of this. So, now if I do not know the width of A, I cannot decide the width, the total width of this B, right. So, I have to I have to decide A first and then B, right. So, but in some scenarios there may be circular dependency. If you try to do B, then you have to do C. If you have to do C, A, and something like this. So, then it will be actually a circular dependency, and there may not be a so you cannot have a basically a specific order, right. So, then in that sometime they basically you need a switch box. So, why you need a switch box? You can actually define some portion of the circuit which is basically switch box, and so that you can actually reduce the dependency, and you can actually make a channel order. Okay. So, once this channel, so there are some other terminology, right. So, now I know the terminals each side, and I have to make the connection. So, you can make this connection. So, this is tracks. So, your objective is to reduce the number of tracks, and so suppose for example, you can make the connection only through one track, or maybe for one connection you may have to needed 2 tracks. This is one track, this is one track. So, that is what is called dog leg, that this, because you cannot go through this, because there will be overlapping here in the track, which is not allowed. So, you probably you have to break this the whole interconnection into 2 parts. This is one part and this is one part, through which you make this dog leg connection. You break the whole connection into 2 tracks. Okay. So, these are the kind of terminology you should aware of, that in a channel the number of pin configuration is given, and what are the connections I have to make, that is also given, and you try to put all these connections in minimum number of tracks. Okay. And this is something, and sometime you make the connection, the whole connection in one track, or you have to split it, and which is called dogleg. Okay. And your layer maybe there might be 2 layers, or maybe you have to make all the connection into one layer, or you may have the horizontal is one layer. So, you have one horizontal layer followed by one vertical layer. So, that whenever you are going from the horizontal to vertical, you go through some via, right. You can understand that there is this is horizontal layer. So, you make the horizontal connection here, and then suppose I have to make the vertical connection in this layer. So, I have to make a connection through this, which is through via to this, right. So, which is called VH or HV, maybe horizontal up, then vertical up, then horizontal, or horizontal and vertical like this, or maybe you have a 3 layer, 2 vertical layer, 1 horizontal layer, or 2 horizontal, 1 vertical layer. So, these all things are possible. Again I am not going to going into detail of this, but when you are actually working on the channel routing problem, these are the terminologies should come to you, right. And your channel routing problem is, as I mentioned, there are 2 vector of same length pins are there, the pins are given of 2 side of the channel, and there the number of layer is given, whether it is a VH model, HV model, HVH model, and those that is also given, and you actually, and the pin number. So, if this is 1, this is 1, and this is 1, that means you have to make the connection like this, right. So, whatever the pin number, that will actually have to connect those. So, if this is 2, this is 2, that means I have to make a connection through this, right. So, this is also given to you, and you have to make the connection pin together and minimize the total channel width, number of vias, width means the number of tracks, right. The number of channel width means the number of tracks, and also you try to make a lot of the vertical connection also. This vias means you have to make a vertical connection, which also you try to reduce. Okay. As I mentioned here an example. So, this is 1, this is 1, this is 1, and this is I have to make a connection like this, right. Similarly, this is 2, this is 2 means I have to make a connection like this. So, this is what is how the problem is given. You just given this set and this set, right. This is and you have given whether it is a VH, HV and this, and you have to solve this, right. So, you can see here there can be various constant, right. So, if you have a this and this, that means they cannot be put in the same track because they are overlapping. So, this is horizontal constant. You can construct a constant graph like this. For example, this 5 this and this 5 and 4, they have overlapping. So, 5 to 4 have a edge, right. Similarly, so this is horizontal constant. Similarly, if 0 of there, so you cannot, they are actually do not cross in horizontal line, right. For what I am trying to say is that if 6 is there, so basically say 1 to 3, right, 1 to 3 there is a connection. So, that means whatever the connection is happening, say 1 to 1, this 3 cannot go here, right. So, you cannot go across this. So, if this is the track say 2, the connection from 3 has to happen below this, at least from 3, it cannot go crossing this, right. So, that is what is called vertical constant. So, you should have those, you can actually extract out those vertical constant and horizontal constant, and using that actually you can solve your problem, and you can actually identify the number of minimum track required using some logic also, which is the channel density. So, those kind of approach, and there are lot of algorithm is also there, left edge algorithm and other kind of solving algorithm, which actually can handle dog leg connections or say VHB model and all. Again, I am not going to detail of those algorithms, but just to give you the problem flavor, what is the channel routing problem and what is happening here. Okay. Similarly, we have a switch box routing. I just talked about switch box in channel because it has only 2 kind of side, upside and downside, but in switch box I have connection in all from all 4 sides. So, it is a more complex problem. So, that is also there. So, in summary, I have discussed about this physical synthesis flow. I give a very brief overview of this physical synthesis, what is placement, what is floor planning, what is partitioning initially, and then what is routing, and what is the problem definition there. What I have not covered is that the techniques, the detailed technique in detail, their efficiency, their robustness, those part I have I do not cover here. So, what the objective of this particular lecture is something just to give you the understanding the problem, how to formulate that problem, represent that constant, and how to represent the solution, etc. And you just think about what kind of assumption is there, what are the constants are there, and also how we can fundamental algorithm to solve this problem, like the heuristic based approach, or sometime you need left edge algorithm or those things, or maybe you sometime you will go for genetic algorithm, or sometimes simulated Bayesian learning algorithm. But without going into detail of the solution, we just talk from very overview level, and also this physical synthesis is still relevant in the sense that the world is changing, the new kind of constants are coming like this. You have security constant nowadays, you can have reliability, you can have other new constants like the criticality of your power of those things. So, there is always a scope to evolve some new kind of placement, floor planning or routing algorithms which can actually satisfy this kind of new strategies. Okay. So, with this I conclude this particular module, and thank you.